Okay, so I think we can start. So, hello everyone, thank you for coming. Today we're excited to have Dr. Georgia Nolfo. So she obtained her PhD at Washington University in St. Louis, and she has a lot of experience in experimental astrophysics, and she's also involved in many projects that help to understand, for instance, the acceleration and transport of solar energetic particles. But today she's going to talk about partnering with the Goddard Heliophysics Science Division. So thank you very much for coming, and you will have approximately 45 minutes. Georgia, the floor is yours.
Okay, great. Thank you so much. So yeah, thanks for having me today. I'm really coming to UNH wearing a bit of a different hat today as the heliophysics line of business. So really looking at our strategic new business opportunities. So that's a new position for me. And we wanted to take this opportunity to really talk to you about potential opportunities for partnering. I know it's not new that we are partnering with the University of New Hampshire. I myself already work with the University of New Hampshire on instrument development, but we've been partnering with you since, stereo and now with IMAP. So there's really a lot that we do together, and we're excited about that. But we wanted to take this time really to talk to you a bit about what we're doing at Goddard right now, and what the opportunities might be for partnering, and also really looking at that how we do our new business process. So just in case you aren't familiar with Goddard, we're about 400 engineers and scientists. 80 of us are civil servants. And we like to say that we're the largest single concentration of heliophysicists on the planet. So this is looking at the Heliophysics Science Division from the back of the parking lot. And I think one of the things I'm going to do in this new position is get a new picture. So we do have a vision in Heliophysics Science Division, and that's really to discover and innovate in heliophysics for the benefit of those on Earth and those exploring the solar system. And so we really want to do that by, looking towards opportunities for scientific discovery. Our physical domain is really the heliosphere and beyond. And we're also really interested in the human and robotic space exploration aspect of that. And so we do that, of course, by taking advantage of data analysis, theory, scientific modeling, instrument development, mission development, and other technological innovations to really achieve a new understanding of heliophysics system. But we do need to partner, and we've already been doing that with UNH. We do that with the heliophysics community. We're really looking to, pursue that full systems understanding by really excelling in all the heliophysics subdomains and interdisciplinary connections to the other agency science areas. So this is just, wanted to remind those of you that are less familiar maybe with heliophysics that there are, some overarching questions that we're trying to answer. What causes the sun to vary? How do the Earth, the planets, and the heliosphere respond to those variations? And then there's that societal sort of component of, what are the impacts to humanity? And on the left, I'm just showing our Heliophysics Systems Observatory. And you can kind of see that, to really understand all the different domains of heliophysics requires quite a fleet. We have that fleet. There's something like 20 operating missions and 13 missions that are in formulation or implementation. And really, Goddard scientists support virtually all of the NASA heliophysics missions. So we're very excited to be so engaged in our community. And we kind of think of ourselves as having some key roles at Goddard, and that's to formulate complex missions and as active researchers and instrumentalists, to provide expertise and support in heliophysics and space weather in the community and the federal government. And then finally, to provide critical expertise and infrastructure to address the National Space Weather Plan and the M2M programs. And I'll talk about that in a little bit. So we, again, I'm just saying that we have a very broad range, many domains that really constitute the heliosphere. So to provide that kind of expertise, we have 5 separate branches at Goddard. The Solar Physics Laboratory is really focused on that fundamental science of the sun. The Heliospheric Physics Laboratory takes that those variations at the sun to try to understand how that's influencing our heliosphere all the way to the outer boundary. Then if we move sort of closer at home, we have our geospace physics laboratory and our ionospheric, thermospheric, and mesospheric ITM physics laboratory, really looking at how the sun is, changing that environment and how the energy and momentum are transported in the upper atmosphere. And then finally, we have our space weather laboratory, again, looking at that societal component in terms of how the space weather is varying, both at Earth and at other planets. So our space weather branch, within that, we have our Community Coordinated Modeling Center. And that was established actually in 2000 as an essential element of the National Space Weather Plan. This is a multi-agency partnership that really is there to support the research and development for that next generation space science and space weather modeling. You can see all of the various agencies that work with the CCMC, and we really have now a kind of elevated coordination, I'd call it, with NOAA's Space Weather Prediction Center and the community to kind of enhance that research to operations process. So on the far right, what you're seeing is just one of the capabilities that we provide at the CCMC. And that's all of the modeling that is done through the CCMC. Again, many, many domains are covered in heliophysics, from the sun to the inner heliosphere to the near Earth environment, our magnetosphere, our ITM environment. And you can see all of the various models that come together to really kind of provide us with a space weather umbrella to characterize and mitigate the hazards of for the benefit of our nation. So CCMC, provides modeling capability, but it also provides numerous other things such as simulations and evaluations, applications, space weather services, and even an education component. So one of the other areas that CCMC supports is our Moon to Mars Space Weather Analysis Office. And this is a recently established office to support the NASA Space Radiation Analysis Group, SRAG at Johnson, with the human exploration activities. And so they provide really 24/7 coverage of radiation environment for the Artemis missions to help validate models for radiation prediction. So you can kind of think of this really as a critical support of the human exploration by providing an end-to-end space weather capability. So from that instrument to the observations, to the modeling, to the predictions, and then finally to the real-time forecasting. And so what I'm showing on the far right is our Artemis launch. And again, the M2M office provided 24/7 coverage of that. So it's a really exciting time for us in the Heliophysics division as we were watching that launch and really working hard to provide that coverage. On the upper right, I'm just showing an example of one of the coronal mass ejections that was modeled through the M2M office. It was a recent ejection that was on the backside of the sun, and yet many solar energetic particles were observed towards the Earth. So it just goes to show you how important it is to really have that full view of the modeling to provide that, that kind of space weather analysis that you need as we move into that exploration mode. So we're also, of course, interested in instrumentation. Here, I just wanted to highlight the Hermes Space Weather Suite that is going to be, is on the Artemis. And that is on the right, on the left, I should say, you can kind of see the habitation and logistics outpost, or HALO, as part of that gateway where the astronauts will reside. On the right, what you're seeing is the orbit. The Artemis is going to be orbiting around the moon several times. In that time, it will actually pass through the solar wind and the Earth's magnetotail. So there are a number of goals that it can really address in terms of space weather, to determine the mechanism of the solar wind mass and energy transport, to characterize the energy topology, its ion composition deep in the magnetotail, and then finally to really establish an observational capabilities of an onboard pathfinder payload for measuring the local space weather to support deep space and long-term human exploration. So what I'm showing on the bottom is that suite of instruments. MERIT is one of our instruments at Goddard. It's a solid state-based instrument to measure solar energetic particles. Then we have our electron electrostatic analyzer, also from Goddard. to measure the electrons between hundreds of eV to 10 keV or so. And then we have a fluxgate magnetometer that's in collaboration with the University of Michigan. And then finally, as part of that suite, is a solar wind instrument by Berkeley that's very similar to the one on Parker Solar Probe. So this space weather suite is really exciting, but as you might well guess, we need many measurements to really do a good job of space weather. We need that distributed element to our measurements. So that's something that we're looking forward to really addressing. And also we need next generation instrumentation aimed at filling the existing measurement gaps. So I thought it would be useful to just spend a second talking a little bit about the space weather, landscape, if you will. And we're having this increased presence in space. And so that's really providing an urgent need to safeguard our space assets and our astronauts. And honestly, that's never made more clear than in our National Space Weather Strategy and Action Plan, and also our 2020 PROSWIFT Act. But also we have our National Space Weather Observing Program through NOAA. That will actually now be located. I'm sorry, my phone is going, and there's nothing I can do about that. It will be located here at Goddard. And that's an exciting time, I think, for Goddard and NASA to really be working closely with NOAA. And we will be providing some project science support for that. And then finally, I wanted to highlight also that we have our new space weather, our NASA space weather program, which just got allocated 27 million. So that's a fantastic wedge that we think will be growing in time. So it's a really exciting time to be taking advantage, I think, of space weather. It's not just a problem with the United States. This is an international concern. So of course, we want to work with our partners internationally, and we were already doing that. I think many of you may know about the ESA L5 Vigil opportunity to place a spacecraft at the L5 Lagrange point, which will really provide us with an absolutely new viewpoint to expand our space weather capabilities. So this urgency is kind of amplified by the fact that we're entering into our solar cycle, the solar cycle maximum. So just showing up here on the right that Marshall solar cycle forecast for that. And so we really need to, be able to increase that capability to address that. And then there's also a growing concern for orbital debris. It was mentioned really as one of the top concerns for NASA. There is some money coming into the Heliophysics for this, for understanding orbital debris. And it's also some money has been allocated this year to SDMD to look at that. There may even be a mission in the next few years where we have an opportunity to characterize the orbital debris, particularly even understanding that environment, something that I think the Geospace Dynamics Observatory would be really exciting to aid in that. And I'll talk about that in a little bit. So the Moon to Mars program is an agency priority. The human space exploration demands technologies to aid and protect our astronauts. And again, another really rapidly growing area in space science. I really feel like Heliophysics community is fundamentally enabling to getting humans safely to the moon and beyond. So these kind of space weather endeavors are big efforts, and they really require partnerships both at home and internationally. I also wanted to kind of highlight some of the things that we can do at Goddard. We have our mission design lab and our instrument design lab. And I'm just showing here on the left some pictures of the scientists and engineers that are working in these design labs. And if you haven't done one, they're super fun, but they're a really fantastic way to really mature, I would say, your concept. And we often provide internal funding to do these designs to really get ready for those opportunities ahead of us. We also have our Goddard small sat office, and that's actually providing spacecraft bus and payload technologies, both in-house and out-of-house. Our small sat office has really done a very careful analysis of the capabilities in the commercial sector. So really giving us a great head start on how to move forward with CubeSat opportunities. And here I'm just showing a small subsample of those CubeSat opportunities. Most notably upcoming is the BurstCube mission. That's actually kind of a fun mission because it's a collaboration with heliophysics and astrophysics to look at gamma rays associated with gravitational waves. So that's a very exciting opportunity. And then the Dione mission is another one, a CubeSat that will be looking at the upper atmosphere and how the solar wind is driving the changes in that upper atmosphere. So we also put missions on the International Space Station, and the two upcoming ones are Codex, which will put a coronagraph on the International Space Station. Very exciting to be able to provide that, constant, examination of the sun. And then we have Story, which is going to be putting a energetic neutral atom instrument to look at the ring currents and the dynamics within the ring currents on the International Space Station. And then finally, we also do small sats. So this is just an example of a small sat that is kind of unique in that it combines space and ground assets to provide an adaptive optics beacon that using a commercial laser. So this is going to have applications in astrophysics, but you could well imagine that we could do something like this in terms of improving our angular resolution, perhaps with DKIST. So we also have our Wallops Center, which provides our suborbital platforms ranging and access to space. And there that's really great opportunity to work with them to mature your technologies through these suborbital opportunities. So here we're showing our portfolio. This is our heliophysics science portfolio, kind of organized by the NASA technology taxonomy. So on the very far left, you can see our remote sensing instruments. For instance, we have our UV slit spectrograph UNIS, which has flown many times on sounding rockets. And we have our X-ray detectors and gamma ray detectors. And on the very far right, we have our in situ instruments and sensors. So here we have our magnetometers and our electric field sensors, and then our particle instruments. I've already mentioned MERIT, and some of you will recognize the high energy ion telescope HIT that will be on IMAP. And then in between that is our observatory, sort of bridging those capabilities where we have our mirror systems and structures and antennas. These are also things we're working on. And I will talk a little bit about the details of some of those coming up. One of the things that I will be trying to do is putting together kind of a handout, if you will, to our partners to give you a better sense of these different technologies that we have, so that you might be thinking about how could you fill the gaps, the measurement gaps that you have in your concepts. So as an example, I've already talked a little bit about our magnetometers. That's really a core effort for us at Goddard. On the left, we have our standard fluxgate magnetometer. This is a very high heritage magnetometer. It's a little bit larger and more power, but it's flown 1 million times and is very sensitive measurements. On the right, however, we have our more inexpensive kind of resource efficient approach to magnetometers, where it's mounted on a boom, but then we have inductive magnetometers mounted at the base. And then you can use a more mature noise canceling technique. But this really allows you to miniaturize that technology. And I've already mentioned that this one's going to be flown on Hermes, but it was also selected for the Geospace Dynamics constellation, which I'll talk about. So I also wanted to highlight this one, partly because I'm the PI of this one, but also because we're collaborating with the University of New Hampshire on this. And these are to develop some neutron spectrometers. So on the left, we have our Lunar Outpost Neutron Spectrometer, LUNS on the moon. That is really a traditional double scatter neutron spectrometer. It's composed of organic scintillators that are read out by arrays of silicon photomultipliers to provide us with some coarse imaging and energy sensitivity between 0.5 and 100 MeV. And we would envision this flying either on a CubeSat or on the surface of the moon. And then on the right, we're really highlighting here our an instrument that started at the University of New Hampshire, and we're now getting the opportunity to really mature this technology called SONTRAC, or Solar Neutron Tracker. And here you can kind of see a picture where you're seeing orthogonally stacked scintillating fibers, and those fibers are actually getting read out by similarly pitched silicon photomultipliers. You can kind of see that array on the lower right. And if you can use the kinematics of elastic scattering, you can uniquely determine the incident neutron direction and its energy. So that instrument is really ideal for doing some imaging to reduce the background and identify solar neutrons. So finally, the other one that I wanted to highlight is our diffractive optics. So, diffractive optics provides really unprecedented angular resolution compared to more traditional approaches. So on the very top right here, you can see a Fresnel lens, a zone plate, I should say, that uses diffraction to focus light through progressively thinner rings in glass. Right next to it, you can see a photon sieve that uses diffraction to focus EUV through holes etched in silicon disc. So on the lower right, we're showing some work that we're doing to develop an X-ray zone plate, hopefully to achieve 0.006 arc-second resolution in X-rays. This would be 100 times better than the traditional X-ray focusing optics. But the caveat there is that it does require large focal lengths on the order of 100 meters or so. And then on the right, I'm actually showing a photon sieve concept. So this is composed of 52 million holes. They're with diameters that vary between 2 and 144 microns that are etched in a silicon disc, and you can kind of see the etch pattern right below that. And this will really enable diffraction limited angular resolution in EUV at unprecedented less than 10 milliarc seconds. And that's really providing us with 10 to 50 times the resolution of Solar Dynamics Observatory. And this will actually be flown on a technology demonstration with two 6U CubeSats called Visor. So it's a really exciting opportunity to test this technology in preparation for a bigger mission. So I did want to take a second to just talk a little bit about Geospace Dynamics Constellation. If you're not familiar with it, it's a constellation in low Earth orbit of 6 satellites that will really provide us with the first global view of the Earth's upper atmosphere. It's really our final flagship recommendation for LWS coming out of the 2013 Decadal Survey. And we've really made a lot of progress on this mission. We had a year-long pre-phase A study, and then we've now moved into the phase A. Interdisciplinary scientists have been chosen. The instruments themselves have been chosen, and I'm sort of highlighting them on the right here. I think you might recognize the Fluxgate magnetometer, which is in collaboration with the University of Michigan, has been partly developed here at Goddard. And then we have another thing you'll recognize is the dual top hat electrostatic analyzer. Now we are providing both electrons and ion capability. And then we also have a quadrupole mass spectrometer to really look at that neutral and ion species in the ionosphere and thermosphere. And then there are 2 other instruments that are provided. Ether, that is looking at the thermal electron density and temperature measurements, and the thermal plasma sensor, which will be looking at electron energy flux and density. And so Goddard will be providing both the management, real-time space weather stream, and of course I've said some of the instruments, but I just kind of wanted to make a pause, no pun intended here, to just talk a little bit about the FY24 budget, which has recommended a pause in the GDC funding. So this is just a really important time, I think, for a community coordinated response to really talk about how important the science is coming out of GDC, particularly because GDC is going to be providing us with that kind of space weather context, to do a better job at safeguarding our assets in space. The other thing that I think is exciting about GDC is that it's going to be kind of serving as a strategic hub. And many of the scientists at Goddard are leading this effort, where you can kind of envision having space-based missions, ground-based measurements, simulations in theory, and then sounding rocket balloons and CubeSats, all kind of coming together to form a great ITM observatory that kind of feeds into a greater heliophysics observatory, all working together. So it's really an exciting time to build our understanding of the upper atmosphere, how the sun is impacting it, and how its response drives space weather. So I also wanted to just take a moment to kind of look at our landscape, where are we headed? And so I sort of put together a heliophysics roadmap. So this is undoubtedly familiar to many of you. Up at the very top, we have our flagship missions. I've mentioned that IMAP is well on its way, past its CDR recently, and we expect it to be launched in 25. GDC, we're hoping will have minimum, impact to the pause. And then we're kind of all, I think, anxiously waiting for the results of that decadal 24 survey, which hopefully will come out in the summer of 24. To sort of tell us, what are those big missions going to be that the community is really expressing a need for? Will it be interstellar probe? Will it be solar polar probes? Do we need distributed missions? Where are we going with that? And then there are some kind of, exciting missions. I've mentioned Del5 already. Dynamic is getting started with a concept study to really complement GDC. And so that's an exciting opportunity. And then we have our explorers. I think I already know that University of New Hampshire is anxiously awaiting the step 1 results. And we're already starting to go ahead and look ahead at the MIDEX opportunity, which should be coming out, that AO, in FY25. And then there are these exciting opportunities for the Moon to Mars program, which we can do through the Artemis and PRISM opportunities to really put instruments in cislunar, around the moon, and on the surface of the moon. And as I mentioned earlier, the space weather program is really increasing. There's opportunities there to get involved in putting instruments up there in terms of our space weather instrument pipeline, the NOAA Next SWIFO series. And as I've mentioned, also orbital debris is really becoming an increased interest. And then finally, our sort of bread and butter opportunities are H40 and LCAS, where we can put our suborbital and our CubeSats together. So for us, really, there are those less expensive opportunities that can do really great science. And then there are the really long-term opportunities. What's that decadal survey going to tell us about our flagship missions? What opportunities can we work together on for the Moon to Mars programs, as well as the space weather programs, where we really need those distributed measurements? So I wanted to now take a little bit of time to talk a bit about our new business process. It's a little bit complicated. And so here I'm just kind of showing that Goddard is sort of divided into 7 lines of business. There are 4 lines of business for the sciences, so earth science, astrophysics, heliophysics, and planetary science have lines of business. And then we have what we call our enabling lines of businesses, which are our suborbital platforms and ranging services, cross-cutting technologies, and communications and navigation. And so we all work together, we meet regularly to sort of provide both a kind of strategic and tactical oversight to help the center meet the overarching business goals. So this is what I really wanted to take some time to talk about. It's an eye chart, and I guess if there's one thing that I want you to take away from this, it's that our process takes a long time. So if you start at the very top with our strategic positioning phase, this is kind of where we start with the line of business. So our heliophysics line of business, we put out a call for concepts almost 2 years prior to the expectation of the AO. So for an example, we will be putting out a call for concepts for the MIDEX opportunity this summer. So getting involved with us at this time for that MIDEX is really the right time to work with us. And the way that it works is that we tend to put out a call, maybe a couple, will be refining those calls, we'll be prioritizing them, and then inevitably we'll be putting forward between 2 and 5 of these concepts to go through the process of trying to get some bid and proposal funding. So that kind of starts very early, and then that leads us into that second row, which is highlighted in blue, which is our concept development phase. And so here, once the LOB has recommended their concepts that they're putting forward, we then have to go through 2 gates. It's the Strategic Science Concept Review and also the Strategic Business Council Review. And so these 2, gates, if you will, or reviews, are really looking at whether or not we have high quality science concepts and are they strategically important to the center and to NASA. And so they're very important. But once we kind of get through those 2 gates, then we are able to provide some bid and proposal money. that bid and proposal money is limited. So of course we have to go through these, these various gates, but then we kind of enter into a phase. And I just want to point out on the very far right, you can see that this is already 12 months in advance of the release of the AO. Then we start entering into this phase that may be more familiar to some of you, our technical and management review, which we call TMR, which is really looking for a point solution to your concept. Do you have sufficient margin? Are your payloads, do they have the field of views they need? All of those things that really contribute to a point solution. And then the other sort of gate is our proposal authorization review, our PAR. This is where we're really doing a cost analysis. And so here we're really concerned with whether or not, the concept fits within our cost cap. So at that point, once we have passed all of those 4 reviews, we are then ready to start writing our proposal. And that really begins when the AO is released. And typically you then have 3 months to write your proposal. And there are a couple of other reviews that we provide. I'm pretty sure that UNH does the same thing. We have a blue team and a red team. Typically, those are the only 2 we do. That are really looking at, the winnability of the science, the compliance, how the messaging. And then once the document is ready, there is a final gate called the executive review that we have to go through in order for the center to sort of say, can we deliver on this particular concept? And once that review is passed, then of course we go through our signatures and we can submit the proposal. And then on the bottom, I'm sure that you're more familiar with headquarters evaluation phase, where we have our step 1 and our step 2 selections. If you have a Goddard PI-led effort, then we would be providing some of that bid and proposal support through that site visit. So just to summarize, there really are 5 gates that we have to go through. We have a limited amount of resources. Once you pass several of those gates, we provide proposal manager, formulation manager, proposal production support. We do provide engineering support depending on the maturity of the concept. There are some monthly reporting that we have to do, sort of these status reviews. They're kind of similar to MSRs for missions that are in implementation phase. And then finally, just to remind you, we do have to get center approval before submitting the proposal. So in a nutshell, what I really wanted to summarize here is that the LOB call for concepts is long and long before the AO is released. And so getting involved with us early is, what we're hoping for this. And again, the MINEX is coming up in FY27. We're really getting geared for that. And we're expecting that there will probably be some mission of opportunities as well. So really to summarize, we're really excited to be partnering with you, looking for new ways to do that. We have numerous resources and expertise to bring to bear in our partnership. We think there are a lot of opportunities ahead of us. And if you want to get started working with us, you can either reach out to me as the line of business manager or to our division management, such as Antti Pulkuken, and I think he's here, as well as Gina DeBraccio. Or you can directly reach out with your colleagues at NASA, who will probably engage that LOB process themselves. So really, in summary, Goddard's new business process starts early, and the partnerships need to start even earlier. And I kind of just want to end with, I love this chart, and Nikki Fox always shows it, but we definitely are entering into our heliophysics big year with solar eclipses, Parker solar probes closest approach in 24, IMAP and the Carruthers mission launching in 25. So I agree, this is an exciting time to be a heliophysicist, and we're really looking to partnering with you. So thank you for your time, and I'm happy to answer questions. It's funny, I can't hear any of that, but I can see some clapping.
Is there any question in person first, maybe?
Nope.
Is there any question? Yeah, go ahead.
There are so many positions and the steps. The people who are involved in this, do you guys sometimes get confused? Like, is it like, yeah, how? It's a lot.
All the steps to accomplish it.
Is there like a flow chart everywhere in the office? Like,
Yeah, I don't know. It's the same process over and over again, and it is lengthy and complicated. And that's why I'm here today, to kind of explain our process to you. But as you come from the outside, we will certainly be walking you through that and holding your hand a bit because we're a bit familiar with that. So, the message that I think you really need to take away, I hope, is that we want to engage in these discussions really early. And then, work with us, work with our line of business. There are lots of things we can do. We can work together to mature instrumentation that we're excited to do, either instrumentation that we can offer you. We have internal funding to make that happen, or we can just work with you on maturing a concept. But yes, it's a complicated process.
For the right reason. Yeah.
Actually, how many people are involved in that 2-year process?
Well, my line of business, I mean, that's a kind of a good question. We range from about 10 to 12 people on the team. So that's the team that I'm running. But then we report to a new business council, which probably has something like 20 people on it. And so there's a lot of people involved in this, but there's a lot of different stakeholders. There's the stakeholders that are in the Heliophysics division, which is sort of run through our line of business and our management. And then we have our center management, which is concerned about whether or not Goddard can commit to these concepts. So there's a lot of people involved in it. But it all starts with you guys and with the scientists and the instrumentalists.
And the ideas can be like proposed in any time, or is there like or time of the year that you guys collect all of them and the window closes and you have to wait for the next year to submit your idea?
That's a really good question. I mean, we will make a call for concept. Probably, it will last a certain amount of time. We'll collect all those ideas, and then we will start to refine and kind of prioritize them. And generally, we will put out a few more calls for concepts for the same thing. So give people an opportunity to really think about it. But at some point, it does get closed for that concept because we have to dedicate that bid and proposal money. So we're going to have to prioritize them and move them forward, deciding how they're aligned with, the goals, our near-term and long-term goals. What do we want to do? So it's not kind of a rolling thing. And that's a little bit why we want to come to you and explain to you that the sooner you start talking to your colleagues in our Heliophysics Science Division, the better it will be, because they're going to be more aware of those call for concepts and their various schedules. But I'm already letting you know that this summer we're going to be starting up with our mid-X opportunities.
Can I ask one more real quick?
Yeah.
I'm sure it varies year to year, but is it some information you can share with us, like in general, statistically, how many like concept ideas you get, but how many ideas get turned down, stuff like that?
I mean, that's a great idea. And I'm going to confess that I'm new. But I would say that, looking at the past year, and I've only been on this thing for about 3 months, it looks to me like, maybe we get 8 concepts on occasion, and we may be able to push 3 or 4 through. And even of those 3 or 4, they may not make it through all those gates, right? I mean, there are a bunch of gates that we have to go through. So, I suspect we try to be generous early, because we want those great ideas. We want to mature those great ideas. And I see John Cooper's got his hand up.
Yes. Hi, Georgia.
Hi.
Great presentation. I want to say hello to Jim Connell out there.
Oh, yeah.
Who's a big instrument guy, and Harlan Smith, if he's there. I am retired emeritus at Goddard, but I just did want to mention one part of the Heliophysics division. You've got the instrument side, you have the modeling side of CCMC, and you also have the space physics data facility. So, like all roads lead to Rome, all of the non-solar heliophysics data is supposed to be flowing into SPDF and its various services.
You are right, John. Yep. Very good point. Thank you.
Yes, and there are people there, that can help out, with data management plans and things like that. And there are people coming in, the younger people, not me, that know about artificial intelligence and data mining and all those things. And when I think of terabytes of data coming from all these missions, I just can't imagine that anybody with a computer could figure that out. So
It's true. And that's a really good point. I'm going to add it to my talk. Thank you, John.
you're welcome.
Is there any other question online in person?
Kind of a personal question. I live in Maryland, so Goddard in Greenbelt, right?
Yeah.
If I were to like come up to a building, like is there like a tour for like future space visitors?
So it's a complicated question. I mean, there's the science center. You can go, there's like our visitor center. You can go there without a badge. But I would be happy to give you a tour. So if you let me know, I have to get you a badge. So you can't just impromptu show up, because it used to be if you're a US citizen, you could just show up, but things have changed. And so we need a little bit of a few days heads up to do that.
Right, you might be getting an email from me, just a heads up.
That's fantastic. Great.
Empty.
Yeah, and then she confirmed that they're always happy to do tours. So yeah, just know that. Okay, so I think we're out of questions. Well, thank you very much again for our very clear presentation, Georgia.
Yep.
Yeah. Thanks for having me. Next time I'll try to come in person.